Lectures. Getting into this molecular orbital theory. I love this stuff. This is so cool. More continuation of things from general chemistry. And we're going to put a little PChem twist on it. All right. So let's get into it. And so we're going to start our discussion of molecular orbital theory by describing the H2 plus molecule. So that's about as complicated of a molecule as we can do, okay? And so let's set it up. So here is our physical picture. So here we have one hydrogen atom. Oops. We've got one hydrogen atom right here with a positive charge in the center. Call it atom A. And then here we've got another hydrogen atom. We'll call it atom B. And that, of course, also has a positive charge right here. And it's sharing, both of these atoms are sharing one electron. So it's the H2 plus molecule. And so we're doing H2 plus because, remember, electrons will interact. And adding that extra term into our operator makes it impossible to solve without approximations. Okay, so we start by first describing H2 plus and make approximations from there. Okay, so here is our Hamiltonian operator, right? We know that we've got a kinetic energy term, and it's the same as what we've seen before, negative h bar squared divided by 2me times del squared, where we know del squared is the second derivative squared in terms of xyz or in terms of r theta phi, right? And then now we also know that we've got a potential energy term right there, which you can see is listed right here. And it's entirely due to Coulomb's law, okay? So our potential energy operator, you notice here that there's no angular momentum terms in here because as it turns out, these two nuclei are in close enough proximity to each other that it's Coulomb's law that dominates, okay? And so we notice here that we've got a 1 over Ra1, and so that's going to be the distance, right, between the electron and atom A. And we've got an Rb1, that's going to be the distance between also the shared electron and atom B. And what you'll notice here is, right, there's a negative term right there, okay? So when that distributes through to this Ra1 or Rb1, those are attractive terms, right? The electron is attracted from its opposite charge, right? Negative and positive, it's attracted to atom A, but it's also attracted to atom B. And then now notice we've got this negative 1 over r term, right? So when I distribute that through, I've got a negative and a negative sign. I'm going to get a positive e squared 4 pi epsilon naught over big R, which you can see right there. And that is the repulsive term between the two positively charged nuclei, okay? So there's three kind of effects going on here, right? There's the repulsion of the two nuclei. There's the attraction of the electron to atom A, and there's also the attraction of the electron to atom B, all right? And so, of course, as we do, right, we would solve the Schrodinger equation for this situation. And a solution does exist for this. However, it's complicated, and it can't be extended to polyatomic molecules or ions. So more than just our simple linear molecules, okay? So several approximations have to be used. So the main approximation that we're going to discuss in MO theory is known as the LCAO-MO. And that is the linear combination of atomic orbitals to form molecular orbitals, okay? So, and it goes like this. We're going to come up with a wave function that we're going to call psi plus minus. And we're going to call it plus or minus because we don't know which is which with arbitrary precision. And Pauling says we have to change the sign of the wave function if we change its label. So we include a plus minus there because we have to look at both solutions. We have to look at the positive solution, so psi plus, and we have to look at the negative solution, psi minus, which is achieved, psi plus is a normalization constant times a plus b. That's the linear combination of atomic orbitals. And of course, psi minus is then the normalization constant n times a minus b. Okay. Well, so I'm using a very simple nomenclature here. Okay. And just to give you all of the nomenclatures that are used, A is a wave function, so I'll put the ket around it. Okay. And that's the same nomenclature as chi H1SA, so that is still a wave function. So chi is used in place of psi. I don't make this stuff up. I'm just the messenger. And of course, hydrogen, 1s electron, and A, meaning that it's atom A. And this should all look familiar to us, right? This is our hydrogen ground state wave function, right? Hopefully you've got this tattooed on your forehead by now. Okay, so then B, right? We know that we can come up with a B wave function. And same nomenclature as just calling that chi H1SB. And then, of course, it's going to be the same wave function. But now keep in mind, look, where these are different are in the radii. Okay? And, of course, using our polar spherical coordinate system, if we arbitrarily define RA1, then we can define RB1 in terms of RA1 and in terms of R. Okay? And so again, we've made this lovely triangle so we can follow Pythagoras to get this coordinate system. Okay? So of course we would plug this equation into right here, and we could just leave this as RA1. And when we put this whole thing together, we will have our wave function in terms of, just one of these radii. That's all we would need to specify. And of course, the internuclear distance. All right. And once again, we're going to define this internuclear axis as the z-axis, just like in valence bond theory. So if I was setting up my coordinate system here in Cartesian space, right, the axis between the two nuclei is z, and one of these is x and one of these is y. Okay? And just like we did for valence bond theory, there's going to be a convenience of converting this to a Cartesian coordinate system. And I'm just going to